Hello everyone. It is an audio recorded lecture of class 11's chemistry from NCERT book. The name of the chapter is hydrogen. Hydrogen, the most abundant element in the universe and the third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as a diatomic molecule and is called dihydrogen. It forms more compound than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance as you will learn in this unit. First topic is position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that the elements in this periodic table are arranged according to their electronic configuration. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration of alkali metals, which belongs to the first group of the periodic table. On the other hand, like halogens, it is short by one electron to the corresponding noble gas configuration, helium. Hydrogen therefore has resemblance to alkali metals, which lose one electron to form unipositive ions, as well as with halogens, which gains one electron to form uninegative ion. Like alkali metals, hydrogen forms oxide, halide and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Del IH of lithium is 520 kJ mole inverse. Fluorine is 1680 kJ mole inverse and that of hydrogen is 1312 kJ mole inverse. Like halogens, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogens, it differs from them as well. Now, the pertinent question arises as where should it be placed in the periodic table. Loss of the electron from hydrogen atom results in nucleus of approximately 1.5 into 10 raised to power minus 3 pm size. This is extremely small as compared to normal atomic and ionic size of 50 to 200 picometer. As a consequence, H positive does not exist freely and is always associated with other atoms or molecule. Thus, it is unique in behavior and is therefore best placed separately in the periodic table. Next topic is dihydrogen. Occurrence of dihydrogen. Dihydrogen is the most abundant element in the universe, that is 70% of the total mass of the universe, and is the principal element in the solar atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it is much less abundant in mass in the Earth's atmosphere. Of course, in the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plant and animal tissue, carbohydrates, proteins, hydrides, including hydrocarbon and many other compounds. Next topic is isotopes of hydrogen. Hydrogen has three isotopes: protium, deuterium, and tritium. Can you guess how these isotopes differ from each other? These isotopes differ from each other only in respect to the presence of neutrons. Ordinary hydrogen, that is protium, has no neutrons, deuterium has one, and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical method. The predominant form in protium terrestrial hydrocarbon contain 0.0156% of deuterium, mostly in the form of Hd. The tritium concentration is about 1 atom per 10 raised to power 18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta particles. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reaction, mainly due to their different enthalpy of bond dissociation. However, in physical properties, these isotopes differ considerably due to their large mass difference. Next topic is preparation of dihydrogen. The first method to prepare dihydrogen is laboratory preparation of dihydrogen. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid, and it can also be prepared by reaction of zinc with aqueous alkali. Next, we can prepare it commercially. The common use process are outlined below. First is electrolysis of acidified water using platinum electrodes gives hydrogen. High purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reaction which takes place at anode is 2Cl negative gives Cl2 plus 2 electrons, and at cathode 2H2O plus 2 electron gives hydrogen plus 2 OH negative. Reaction of steam on hydrocarbon or coke at high temperature in the presence of catalyst yields hydrogen. The mixture of carbon monoxide and hydrogen is called water gas, as this mixture of carbon monoxide and hydrogen is used for the synthesis of methanol and a number of hydrocarbons. It is also called synthesis gas of syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspapers, etc. The process of producing syngas from coal is called coal gasification. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixture with steam in the presence of iron chromate as catalyst at 673 Kelvin temperature. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. Presently, approximately 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solution, and 1% from another sources. Next topic is properties of dihydrogen. First is physical property. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical property, along with those of deuterium, are given in the table. Next is chemical property. The chemical behavior of dihydrogen is determined to a large extent by bond dissociation enthalpy. The hydrogen-hydrogen bond dissociation enthalpy is the highest for a single bond between two atoms of any element. What inferences would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atom is only about 0.081%, around 2000 Kelvin, which increases to 95.5% at 5000 Kelvin. Also, it is relatively inert at room temperature due to the high hydrogen-hydrogen bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does not combine with almost all the elements. It accomplishes reactions by loss of the only electron to give H positive, gain of an electron to form H negative, and sharing of electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reaction. Reaction with halogens. It reacts with halogens to give hydrogen halides. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. Next is reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. Next is reaction with dinitrogen. With dinitrogen it forms ammonia. This is the only method for the manufacture of ammonia by the Haber's process. Next is reaction with metals. With many metal, it combine at a high temperature to yield the corresponding hydrides. Next is reaction with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metal into corresponding metals. Next is reaction with organic compounds. It reacts with many organic compounds in the presence of catalyst to give useful hydrogenated product of commercial importance. For example, hydrogenation of vegetable oils using nickel as catalyst gives edible fats. Hydroformylation of olefins yields aldehyde which further undergo reduction to give alcohols. Next is uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dinitrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soybean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol. It is widely used for the manufacture of metal hydrides. It is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydron torches fine used for cutting and welding purposes. It is used as a rocket fuel in space research. Dinitrogen is used in fuel cell for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. Now we will read about hydrides. Dihydrogen under certain reaction conditions combine with almost all elements except noble gases to form binary compounds called hydrides. If E is the symbol of an element, then hydride can be expressed as EHX. Example MgH2. The hydrides are classified into three categories. First is ionic or saline or salt like hydrides. Second is covalent or molecular hydrides. Third is metallic or non-stoichiometric hydrides. Firstly, we will read about ionic or saline hydrides. These are stereometric compounds of dinitrogen formed with most of the S block elements which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as lithium hydride, beryllium hydride and magnesium hydride. In fact, beryllium hydride and magnesium hydride are polymeric in structure. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on hydrolysis liberate dinitrogen gas at anode which confirms the existence of H positive ion. Saline hydride react violently with water producing dinitrogen gas. Lithium hydride is rather unreactive at moderate temperature with oxygen or chlorine. It is therefore used in the synthesis of other useful hydrides. Next is covalent or molecular hydride. Dihydrogen form molecular compounds with most of the p block elements. Most familiar examples are methane, ammonia, water and hydrogen fluoride. For convenience, hydrogen compound of non-metals have also been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons and bonds in their Lewis structure into electron deficient, electron precise, and electron rich hydrides. An electron deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane B2H6 is an example. In fact, all elements of group 13 will form electron deficient compounds. What do you expect from their behavior? They act as Lewis acid, that is electron acceptor. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All elements of group 14 form such compounds, which are tetrahedral in geometry. Electron-rich hydrides have excess electrons which are present as lone pairs. Elements of group 15 to 17 form such compounds. What do you expect from the behavior of such compounds? They will behave as Lewis base, that is electron donors. The presence of lone pairs on highly electronegative atoms like nitrogen, oxygen, and fluorine in hydrides result in hydrogen bond formation between the molecules. This leads to the association of molecules. Next is metallic or non-stoichiometric hydrides. These are formed by many D block and F block elements. However, the metals of group 7 and group 8 and group 9 do not form hydride. Even from group 6, only chromium forms CrH. These hydrides conduct heat and electricity, though not as efficient as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen, for example, LaH 2.87, PDH 0.6 to 0.8, etc. In such hydrides, the law of constant composition does not hold good. Earlier, it was thought that in these hydrides, hydrogen occupy interstices in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, cerium, and other hydrides of this class have lattice different from that of the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction hydrogenation reaction for the preparation of large number of compounds. Some of the metals, example palladium and platinum, can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and as a source of energy. Next is water. A major part of all living organism is made up of water. Human body has about 65% and some plants have as much as 95% water. It is a crucial compound for the survival of all life forms. It is a solvent of great importance. The distribution of water over the earth's surface is not uniform. The estimated world water supply is in oceans it is 97.33%. In polar ice and glacier it is 2.04%. In groundwater it is 0.6% and so on. Physical properties of water. It is a colorless and tasteless liquid. The unusual property of water in the condensed phase, that is liquid and solid state, are due to presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization, and high heat of fusion in comparison to H2S and H2SE. In comparison to other liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment, and dielectric constant, etc. These properties allow water to play a key role in the biosphere. The heat of vaporization and heat capacity are responsible for moderation of the climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to the hydrogen bonding with polar molecule, even covalent compounds like alcohol and carbohydrates dissolve in water. Next is structure of water. In the gaseous phase, water is a bent molecule with a bond angle of 104.5 degree and OH bond length of 95.7 picometer. It is a highly polar molecule. Its orbital overlaps. In the liquid phase, water molecules are associated together by hydrogen bond. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperature, it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation, which ensures the survival of the aquatic life. This, in fact, is of great ecological significance. Structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure. Examination of ice crystals with X-rays shows that each oxygen atom is surrounded tetrahedrally by four other oxygen atoms at a distance of 276 picometer. Next is chemical property of water. Water reacts with a large number of substances. Some of the important reactions are given below. First is amphoteric nature. It has the ability to act as an acid as well as a base. That is, it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with ammonia and as a base with hydrogen sulfide. The autoprotolysis, that is self-ionization of water, also takes place. Next is redox reaction involving water. Water can be easily reduced to dihydrogen by highly electropositive metal. Thus, it is a great source of dihydrogen. Water is oxidized to oxygen during photosynthesis. With fluorine, water oxidized to oxygen as well. Next reaction is hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. Next reaction is hydrates formation. From aqueous solutions, many salts can be crystallized as hydrated salts. Such an association of water is of different types, that is, of coordinated water, interstitial water, hydrogen bonded water, etc. Next is hard and soft water. Rainwater is almost pure. Being a good solvent, when it flows on the surface of the earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with soap easily. Hard water forms scum precipitated with soap. Soap containing sodium stearate react with hard water to precipitate out calcium magnesium stearate. It is therefore unsuitable for laundry. It is harmful for boilers as well because of deposition of salts in the form of scale. This reduces the efficiency of the boiler. Next is temporary hardness. Water hardness is of two types, permanent hardness and temporary hardness. Firstly, we will read about temporary hardness. It is due to the presence of magnesium and calcium hydrogen carbonates. It can be removed by boiling. During boiling, the soluble MgHCO3 is converted into insoluble magnesium hydroxide and calcium hydrogen carbonate is changed into soluble calcium carbonate. It is because of high solubility product of magnesium hydroxide as compared to that of magnesium carbonate that magnesium hydroxide is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. Next method is Clerk's method. In this method, calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide which can be filtered off. Next is permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following method. First is treatment with washing soda. Washing soda react with soluble calcium and magnesium chloride and sulfate in hard water to form insoluble carbonate. Next is Kaljan's method. Sodium hexametaphosphate, commercially called calogen, when added to hard water, the reactions takes place. The complex anion will form which keeps magnesium ion and calcium ion in solutions. Next is ion exchange method. This method is also called zeolite permutate process. Hydrated sodium aluminium silicate is zeolite permutate. For the sake of simplicity, sodium aluminium silicate can be written as NaZ. When this is added in hard water, exchange reaction takes place. Next is synthetic resin method. Nowadays, hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin is changed to RNA by treating it with NaCl. The resin exchanges Na positive ions with Ca2 positive and Mg2 positive ions present in hard water to make the water soft. Here R is resin anion. The resin can be regenerated by adding aqueous NaCl solution. Pure demineralized water-free foam from all soluble mineral salt is obtained by passing water successively through a cation exchange and an anion exchange resin. In the cation exchange process, H positive exchanges for Na2 Na positive, Ca2 positive and Mg2 positive and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, the OH exchanges for anions like Cl negative, HCO3 negative, SO42 negative, etc. present in water. OH negative ions thus liberated neutralizes the H positive ion set free in the cation exchange. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solution respectively. Next is hydrogen peroxide H2O2. It is an important chemical used in pollution control treatment of domestic and industrial effluents. Preparation. It can be prepared by acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. Peroxidized sulfate obtained by electrolytic oxidation of acidified sulfate solution at high current density on hydrolysis yields hydrogen peroxide. This method is now used for the laboratory preparation of D2O2. Industrially, it can be prepared by the auto-oxidation of 2-alkyl lanthraquinols. In case of 1% of H2O2 is formed, it is extracted with water and concentrated to approximately 30% by mass by distillation under reduced pressure. Physical properties of hydrogen peroxide. In the pure state, it is almost colorless, very pale blue liquid. Its important physical properties are also mentioned in the table. It is miscible with water in all proportion and form a hydrate. A 30% solution of hydrogen peroxide is marketed as 100 volume hydrogen peroxide. It means that 1 milliliter of 30% hydrogen peroxide solution will give 100 milliliter of oxygen as STP. Commercially marketed sample is 10V, which means that the sample contains 3% hydrogen peroxide. Next is structure of hydrogen peroxide. It has a non-planar structure. The molecular dimension in the gas phase and solid phase are given in the figure. Chemical properties of hydrogen peroxide. It acts as an oxidizing as well as an reducing agent in both acidic and alkaline media. Simple reactions are described below. Oxidizing action in acidic medium will be shown by the reaction 2Fe2 positive plus 2H positive plus hydrogen peroxide gives 2Fe3 positive plus 2H2O. Reducing action in acidic medium is shown by the reaction 2MnO4 negative plus 6H positive plus 5H2O2 gives 2Mn2 positive plus 8H2O plus 5O2. Next is oxidizing action in basic medium. 2Fe2 positive plus H2O2 gives 2Fe3 positive plus 2OH negative. Next is storage. Hydrogen peroxide decomposes slowly on exposure to light. In the presence of metal surfaces or traces of alkali, the above reaction is catalyzed. It is therefore stored in wax-lined glass or plastic vessels in dark. Urea can be added as a stabilizer. Uses of hydrogen peroxide. In daily life, it is used as a hair bleach and as a mild disinfectant. As an antiseptic, it is sold in the market as perhydrol. It is used to manufacture chemicals like sodium perborate and percarbonate, which are used in high quality detergents. It is used in the synthesis of hydroquinone, tartaric acid, and certain food products and pharmaceuticals. Nowadays, it is also used in environmental chemistry, for example, in pollution control treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage waste, etc. Next topic is heavy water, that is D2O. It is extensively used as a moderator in nuclear reactor and in exchange reaction for the study of reaction mechanism. It can be prepared by exhaustive electrolysis of water or as a byproduct in some fertilizer industries. It is used for the preparation of other deuterium compounds. Next is dihydrogen as a fuel. Dihydrogen releases large quantity of heat on combustion. The data on energy released by combustion of fuels like dihydrogen, methane, LPG, etc. are compared in terms of some amounts in mole, mass and volume. Moreover, pollutants in combustion of dihydrogen will be less than petrol. The only pollutant will be the oxides of dinitrogen. This, of course, can be minimized by injecting a small amount of water into the cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. A cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. Also, dihydrogen gas is converted into liquid state by cooling to 20 Kelvin. These limitations have prompted researchers to search for alternative technique to use dihydrogen in an efficient way. In this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gaseous dihydrogen. Advantage of hydrogen economy is that energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as fuel was launched in October 2005 for running automobiles. Initially, 5% dihydrogen has been mixed in CNG for use in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for generation of electric power. It is expected that economically viable and safe sources of dinitrogen will be identified in the years to come for its usage as a common source of energy. So this is all about the chapter hydrogen of class 11's from NCERT book. Thank you.